Our next speaker is Tianxi Ji, who is going to be talking about privacy-preserving fingerprinting against collusion and correlation threats in genomic data.
Okay, thank you for the introduction. My name is Tianxi Ji from Texas Tech University. Our work is privacy-preserving fingerprinting against collusion and correlation threats in genomic data. This is joint work with Erman, Emery, and Penn. So the construction and sharing genomic data has been significantly advanced. The collaboration research on human genetics and modern medicine. However, genomic data breaches happens every year. One of the most recent data breach happens with the giant geotech company called 23andMe. Perhaps many of you are the customers of this company. And in February 2024, it leaks 7 million people's genomic data. And the hacker even sold the original genomic sequence and their kinship family members to on the darknet. And even worse, the company lacks enough clue to trace the to trace where is the data leakage. Instead, they blame the customers for their minor security lapse. Okay, so since the collection of genomic data involves intellectual efforts from the creator and the content of genomic data is very sensitive, so our work is motivated to prevent the unauthorized redistribution of the data and also protect individuals' privacy. And at the same time, we want to make sure that the released or the shared genomic data have very high utility in order to support data mining or genome-wide association studies. And we mainly consider 3 attacks: random flipping, that is just a random change some of the values in the genomic data, and collusion attack, which means some of the receiver may ally together in order to make a pirate copy of the genomic data in hope that none of them will be traced back. And we also consider a correlation attack because in genomic data, due to biological features, some of the genome entries are correlated, and due to the kinship, individuals are also correlated due to Mendel's law. So people can use this background knowledge to infer where are the potential fingerprint entries. So we mainly use 3 techniques to solve our goal. First is database fingerprinting. It essentially introduces imperceptible marks into the databases. So those marks can be used to prevent illegal redistribution. If there is a leakage, it can be used to identify the source of the leakage, and then trace the traitors who should be accused or should be responsible for the data leakage. Then we also use local differential privacy. It just obfuscates individuals' genomic data, and it can also defend against some level of privacy inferences. And we use Turtle's code, which is one of the most powerful collusion-resistant code that can accuse at least one of the colluder if there are zero colluders. And it has 2 parameters: length of the code and also a predetermined accusation score. So this is our framework. We have a database owner, Alice, who she spent a lot of effort to collect some genome sequence from people, and she wants to share her database to some service providers. And when sharing the data, she will insert different fingerprints at different locations of the genomic sequence. But if there is a malicious user who redistributes the data, make a pirate copy in hope to make some illegal profit, then those marks can be used to accuse this guy for the illegal redistribution. And in addition, so that is a concept of protect the copyright of the data. In addition to that, we also want to make sure the privacy is preserved. And also, we want to support very high utility database mining. Okay, so that's the 3 goals. And the proposed scheme is called GeneScope because it simultaneously achieves copyright protection and privacy preserving. So the design principle also threefold. The fingerprint scheme essentially performs the exclusive OR operation between the bits of the genomic data and the random mark bits. So, and you can leverage the randomness in the fingerprinting process in order to achieve differential privacy, because privacy is essentially achieved by also introduce randomness. So you can leverage the randomness in fingerprinting to achieve privacy for free. And in Turtle's code, you will first generate some parameter P using this distribution, and then generates the binary sequence using Bernoulli function. Okay, so here is the main conclusion. Suppose we have C colluders, and if you generate the Tardos code with length lower bounded and acquisition score calculated as Z, and as long as the number of colluders is upper bounded, and you choose the parameter T in this sequence, then you can first achieve local differential privacy, and then at the same time make sure that the probability of an innocent party being falsely accused is upper bounded by beta 1. The probability of failing to accuse any of the colluders is upper bounded by beta 2. So this is the graphical view of our conclusion. So if you set T in this range, you are guaranteed to achieve a collusion resistant. But if you further constrain the value of T in this smaller range in red, then in addition to the collusion resistant, you can also achieve a privacy guarantee. So we in the paper, we did a lot of quantitative analysis, especially compare with a naive solution, which you only, you first do the LDP perturbation on the data and then inject the fingerprint on the data. So we derive closed form association between privacy parameter, randomness parameter, and the robustness of system and the utility. For example, under the same privacy and the robustness guarantee against the random bit flipping attack and the collusion attack, our scheme only needs to change this much of entries where gamma is some constant, but the two-step approach will change more entries. That means the two-step approaches will compromise utility more given the same privacy and security guarantee. So here are the experiment result. And since we focus on the genomic data, the data set we'll use is a HapMap data set. It consists of 15,000 individuals. Each individual has 156 SNPs. So SNPs is just a point mutation at a single nucleotide at a location of the genomic sequence. Since each SNP includes two nucleotides, one inherited from each of the parent, and then SNP is essentially the number of point mutations at that location. You have two nucleotides, so you can either have 0, 1, or 2 mutations. So essentially, the database of the SNP is represented as a set from choosing value 0, 1, 2, and with 15,000 rows and 100 each columns. Okay. So the first experiment is to evaluate the SNP phenotype association. So in GWAS, it quantifies the association between a phenotype and a SNP using the p-value. If the p-value is very low, for example, smaller than 0.05, then it is considered that this SNP, this point mutation at this location have very strong correlation with the phenotype. So we compare with 3 different baselines. One is the two-step approach. The other two is the LDP only, and the fingerprinting only. So we check the persistence or the accuracy of the first 10%, 20%, and 30% of the SNP that have strong association between a specific phenotype before and after the application of the different mechanisms. And you can see, given the same privacy and utility guarantee, privacy and security guarantee, we always have the highest fraction of the consistency of the association. And we also evaluated against the 3 attacks. First is random change some entries in the database. The second is consider the kinship and the correlation in the database and use that correlation to attack the fingerprint database. The third one is to apply a correlation attack followed by the collusion attack. So for example, in the second figure, we consider increasing number of colluders, and then we evaluate the probability of at least one of the colluders is accused for the redistribution. And you can see the scheme is very robust. And even for the attack that combines correlation attack and collusion attack, we can see our acquisition score is always higher than the determinist threshold. That means even the attacker leverages the background knowledge on the kinship or the correlation and further ally with other colluders to make a pirate copy, they still cannot compromise the fingerprinting scheme. So in conclusion, we developed a gene scope to share genomic databases, simultaneously achieve copyright protection and privacy preserving. So privacy guarantee is achieved by leveraging randomness in the fingerprints, and collusion resistance is obtained by using Taylor's code. And for more interested people, you can also check our concurrent work on the explore utility privacy trade-off in genomic databases using source coding. And thank you. I'm now happy to take any questions.
Thank you very much for the talk. Any questions from the audience? If there's no questions, I have one question to ask. So, how do you associate the fingerprints with the identity of the receivers?
Okay, thank you for your question. So the generation of each fingerprint is through a message authentication code, which is essentially a hash function. So in hash function, we will have a random seed. The random seed is choosing to be the identity of the user. So then you can associate the identity with the fingerprints. Thank you for the question.